There's 8 millimeters of air between these two magnets. And somewhere, maybe between 12 and 30, you asked what was in it. Someone told you springs and rubber bands, or magnetic field, moving on. Or, if you read enough, you found Richard Feynman on BBC in 1983, honestly admitting he couldn't fit the answer into 60 seconds. And quietly, you let the question close. You weren't wrong to wonder. He wasn't wrong to be honest. He just had 60 seconds. We have 20 minutes, and we have the receipts. The BBC archival. Peskin and Schroeder, Chapter 4. Fan. 2023. In Physical Review Letters. Measured to 1 part in 10 to the 12. Tonight, you finish the sentence Feynman started. With the paper IDs on screen, before we open the gap, listen to the man who refused to. I really can't do a good job, any job, of explaining magnetic force in terms of something else that you're more familiar with. 43 years that clip has been on the internet. And for 43 years, most people, including most science channels, have treated it like a closed door. Feynman said no, so the answer must not exist. But listen to what he actually said. He said he could not do a good job in that interview, in those 60 seconds for that audience. He did not say the answer did not exist. He said the answer did not fit. By 1983, quantum electrodynamics had already given the answer. The math was 40 years old. The man explaining it was the same man refusing to. Feynman had literally written the textbook. He just could not put 40 years of QED into 1 minute of broadcast television. So we are not competing with Feynman tonight. We are completing him with 20 minutes and with the paper IDs on screen. By minute 16, you will have the answer he could not finish, with 4 primary sources visible. Before we look between the magnets, look between you and the desk. Put your hand down. Press it. Hard. Feel that solid stop? That is not contact. You have never touched anything in your life. What is actually happening is this. Your hand is a cloud of electrons. The desk is a cloud of electrons. And electrons, every single one in the universe, carry the same kind of charge. Negative. Like charges repel. So as your hand gets close, the desk's electrons push your electrons back. You stop. You feel weight. You feel firmness. But the gap never actually closes. How big is the gap? About 1/10 of a nanometer. Roughly 4 billionths of an inch. Small enough that your nerves report solid. Large enough that, on the atomic scale, your hand and the desk are not in contact. They are in conversation. Look at the scale. The nucleus of an atom is roughly 100 to 1,000 times smaller than the atom itself. If the nucleus were a marble on the pitcher's mound, the electron cloud would reach the back rows of the stadium. Everything in between empty. Except it is not empty. It is field. We will get to that. Now notice what just happened. The magnets in your hand and your hand on the desk are running the same physics. Electrons, pushing electrons. One force, one field. Different geometry. What we just unlocked. Touch is electromagnetic repulsion, not contact. Same force as the magnets, just at a smaller gap. Which raises the obvious next question. If it is one force, what is the force? Not what it does. What it is. So here is the move most physics teachers never finish. The magnet in this hand and your hand on a desk, they are not running two different forces. They are running the same force. Electromagnetism. One force, one field. The only difference is the geometry, how the electrons are arranged inside the material. Inside a piece of iron sitting in your kitchen drawer, the electrons are mostly disorganized. Their tiny magnetic moments, their spins, point in random directions. They cancel out. The iron behaves like a regular metal. Boring. Inside a neodymium magnet, those same electrons have been forced to line up. Their spins march together. Billions of tiny pushes, adding to one big push. Same particle, same force, different arrangement. Think of it like a marching band. One person waving a flag in the park, barely visible. 80 people in a stadium, waving the same flag at the same angle, at the same beat, visible from the top row. The flag did not get bigger. The coordination did. That is what a magnet is. Coordinated electrons. Same physics as your hand on the desk, just lined up. Which means your hand pressing the desk and the two magnets refusing to touch are not analogies for each other. They are the same event at different scales. Both are the electromagnetic field doing its job at a distance. And that is the part most explanations stop at. It is the electromagnetic field. Moving on. But that is not an answer. That is a label. The honest question, the one Feynman would not pretend was easy, is this. What is the field? Not what does it do? What is it made of? What we just unlocked. Magnets and contact are the same force at different scales. One field, two geometries. The answer is the part of physics that won 3 Nobel Prizes. And the man who wrote the textbook on it is the same one we just watched, refused to summarize it. Here is the answer Feynman did not have time for. The electromagnetic field, the thing in the gap between your hand and the desk, between the two magnets, between every atom in your body, is not just a region of space where forces happen. It is a physical object in its own right. It fills the universe. It has energy. It has structure. And like every other thing in nature at small enough scales, it is quantized. It comes in packets. The packets are called photons. Not just the photons of light. You can see every photon, including ones you will never see. And when 2 electrons get close enough to push on each other, what is actually moving between them, carrying the push, is photons. Specifically, virtual photons. Packets of the field, popping in and out of existence in the gap, on timescales so short they cannot be directly detected, about a femtosecond, a millionth of a billionth of a second. Watch this. 2 electrons, coming in from opposite sides. They get close. They exchange. Electron in. Electron in. Wavy line in the middle, that is the virtual photon. Electron out. Electron out. The push happened in that wavy line. The gap was never empty. It was full of the field, and the field handed off a packet. This little drawing has a name. It is called a Feynman diagram. He invented it in 1948. It is not a picture of what literally happens. We will get to that nuance in 2 minutes. It is a way of bookkeeping every possible way 2 charged particles can interact through the electromagnetic field. Every wiggle, every exchange, every correction. Add them all up, and the answer the diagram gives you matches what the experiment measures. By minute 14, I will show you the measurement that matched these diagrams to 13 decimal places. New York to Los Angeles. Inside the width of 1 human hair. So when you press your hand into the desk, this exchange is happening trillions of times per second between every electron in your skin and every electron in the wood. The desk does not push back because it is hard. It pushes back because the field is exchanging photons with you. The hardness is the exchange. This is the textbook, page 89. If you want the math, it is open access in any university library. The wavy line we just drew has a precise mathematical meaning. It is not a metaphor someone invented to make physics feel deep. It is a term and a calculation that, when you do the arithmetic, predicts the measurable behavior of real charged particles in real experiments. Which brings us to the obvious next problem. We just drew a picture of something popping in and out of existence on a femtosecond timescale. How can we possibly trust a thing like that? How would you ever know it was real? What we just unlocked. The field is quantized. The push between charges is carried by virtual photons packets of the EM field. The textbook is Peskin and Schroeder, Chapter 4. The answer involves a single electron, a magnetic trap at Harvard, and a measurement so precise that when QED predicted it, the prediction matched reality to 1 part in 10 to the 12. Most precisely tested theory in human history. But before we get to that receipt, there is one piece of honesty we owe you, because everything we just drew on that whiteboard is, in a very specific sense, not literally true, and the channels that pretend it is are lying to you. Before we go any further, we owe you a confession. That little wavy line we just drew, the one we called a virtual photon, is not a tiny ball of light flying across the gap between 2 electrons. It is not a particle in the everyday sense. It is not even, strictly speaking, a thing that happens. It is bookkeeping. What the wavy line really is 1 term in a long mathematical calculation. Physicists call it a perturbation series. You add up the simplest exchange, 1 virtual photon, then the next simplest 2 virtual photons, then more complicated ones, on and on. Each diagram is a chunk of the math. They are bookkeeping symbols. They keep track of every way the field can move energy from one charge to the other. The man who invented these diagrams wrote a whole book, this one warning people not to take the pictures too literally. He said, in plain English, that nature is stranger than the cartoons we draw of it. So here is the line we will not cross. We will not tell you a virtual photon is a literal object zipping across a literal gap. That would be a useful lie, a pedagogical scaffold. Many channels say it that way because it is easier and it makes them sound certain. We will not. What we will tell you is this. The field is real. The math is real. The predictions the math makes are real to a precision no other theory in human history has ever come close to. The picture is a scaffold. The structure is the field. What we just unlocked. The diagram is bookkeeping. The field is the thing. We do not pretend the cartoon is the truth, which brings us to the receipt. Because if the field is real and the math is real, then somebody, somewhere, must have measured it. And they did. To 1 part in 10 to the 12. In a basement laboratory at Harvard, a team of physicists took a single electron and trapped it inside a magnetic cage called a penning trap. No other particles, no air, no light. Just one electron, held in place by magnetic fields for months. Then they measured it. Specifically, they measured something called its magnetic moment, how strongly that one electron responds to a magnetic field. QED predicts this number. The prediction is not vague. It is a long calculation that uses the Feynman diagrams we just drew, the single virtual photon, +2, +3, plus thousands of more complicated ones. You add them all up, you get a number. The number the calculation gives you and the number the measurement gives you agree to 1 part in 10 to the 12. Let me put that in plain English. Take the distance from New York City to Los Angeles. Roughly 2,450 miles, about 3,940 kilometers. The prediction QED makes about a single electron, and the measurement that team got out of their basement agree within the width of one human hair laid across that distance. That is the paper. Fan and colleagues. Physical Review Letters 130, 71, 801, published in 2023. Pull it up. Read it. The math is in the supplementary. The trap design is in Figure 2. That level of agreement between a theory written with abstract bookkeeping diagrams and a measurement taken in a basement on one particle is the most precise prediction any theory in the history of science has ever made. Not in physics. In any field. Of any kind. Which means whatever virtual photons really are bookkeeping, scaffold, term in a calculation, they are bookkeeping that works to a precision no other description of reality has ever achieved. What we just unlocked. QED predicts a single electron's behavior to 1 part in 10 to the 12. Most precise prediction in human history. The receipt is FAN 2023, PRL 130. So the field is real. The math is real. The measurement matches. But there is still one piece missing from the gap. Because if the only thing in there were virtual photons pushing electrons apart, every atom in your body, including the ones holding this script together right now, would have collapsed nanoseconds after the universe began. There is a second guardian in the gap, and a mathematician proved it must exist in 1967. There is one more thing in that gap, and without it, you would not exist. Virtual photons explain the push. They do not explain why every atom in your body has not already collapsed into a tiny dense lump. Because here is the problem. Electrons are attracted to the positively charged nucleus. By the rules we have given you so far, they should spiral straight in. They do not. And the reason they do not is not electromagnetic. It is a rule called Pauli exclusion. In plain English, 2 electrons cannot occupy the same quantum state at the same time. Think of it like parking. Every electron needs its own spot. No doubling up. So when one electron is in the innermost orbital, the next has to take the next one out. And the next. And the next. That is why atoms have shells. That is why matter has volume. In 1967, 2 mathematicians, Pauli Dyson and Andrew Lenard, proved it. Not argued, proved, with a theorem. They showed that without Pauli exclusion combined with the Schrödinger equation, every atom in your body would collapse in nanoseconds, billionths of a second. The fact that you are sitting here, reading this solid, in one piece, taking up space, is, mathematically, a theorem. So the gap between you and the desk is not just held open by photon exchange. It is held open by a quantum rule that says no 2 electrons may share the same dance. Field. Plus geometry. Plus exclusion. That is the gap. What we just unlocked. The field pushes. Pauli holds the electrons apart. Dyson and Lenard proved, in 1967, that without both, every atom would collapse in nanoseconds. Now we have everything. Every piece. Every receipt. Look at the gap one more time. Now look at the gap one more time. 8 millimeters. Paper sliding through. It is not empty. It is the quantum electromagnetic field, filling every cubic millimeter. carrying virtual photons between every charge in the universe exchanged about 10 to the 42 times more strongly than gravity. A trillion times stronger than the force pulling you toward the center of the Earth right now. It is Pauli exclusion, holding every electron in its own quantum spot, stopping every atom from collapsing. Mathematically proven. In 1967, it is Schrödinger's equation, determining where every electron sits, what shells it fills, what shape every molecule in your body takes. Same physics, same field, same gap. Every cell in your body, every breath you have ever taken, every heartbeat, every time you pressed your hand into something and it pushed back. Same field, same gap. You are not made of stuff. You are made of fields. You are not separated from the world by empty space. You are coupled to it by the same field that the magnets in your hand are coupled by. You are the force you are feeling. Feynman could not say this in 60 seconds in 1983, but it was always true. What we just unlocked. Empty space isn't empty. Virtual photons. Pauli. Schrödinger. One field. And you are the force you are feeling. Which brings us to one last thing. Because knowing this does not stop at the screen. It belongs at a dinner table. Next time you pick up two magnets, really pick them up, you will know what is between them. Not springs, not rubber bands, not empty space. A quantized electromagnetic field. Virtual photons popping in and out of the gap, exchanged about a trillion times more strongly than gravity. Pauli exclusion holding every electron in its own quantum spot. Schrödinger's equation drawing the shape of every atom. Same field, same gap, in your hand, in your body, everywhere. But here is the gift. Tonight, at dinner, on the kitchen counter, in the living room, hand a magnet to someone you love. A child, a parent, a friend, anyone. Ask them, what do you think is in this gap? Let them guess. Let them say springs. Let them say rubber bands. Let them say empty space. Let them say, I don't know, nobody ever told me. Then tell them. Tell them about the field. Tell them about the virtual photons. Tell them about the single electron in a basement at Harvard, measured to 1 part in 10 to the 12. Tell them that they are made of the same thing. Watch their face. That is the video. That is the gift. That is how you carry Feynman forward, not by repeating his refusal, but by completing the sentence he started. If this gave you something to carry, something to hand to someone tonight, subscribe, so we can keep making these. Next video. Why a single photon takes every possible path through this universe to reach your eye. Until then, go find a magnet. And remember, there is no empty space. There is only field.